The idea that a black hole, the most dominant structure in the known universe, could slowly evaporate and disappear sounds like a contradiction. After all, black holes are defined by their insatiable hunger, by their ability to trap light, matter, and even the fabric of space itself. They are, by every conventional understanding of astrophysics, the ultimate endpoints of cosmic evolution. So when Stephen Hawking stood before a chalkboard in the early 1970s and proposed the exact opposite, that black holes might eventually vanish, the scientific community paused, blinked, and collectively asked. To understand why this notion was so shocking, we must return to what a black hole truly is. To a distant observer, it would appear that the black hole was emitting radiation, energy that should be impossible to escape, but the mathematics worked. The escaping particle carried positive energy, and to maintain conservation laws, the black hole had to lose an equivalent amount of mass. If black holes can evaporate, where does the information go? According to quantum theory, information about the physical state of a system can never be truly lost. Yet a black hole, by definition, seems to erase all such details. Researchers began building systems in the lab that mimic the behavior of event horizons, using sound waves, light pulses, and ultra-cold matter. These are states of matter formed when atoms are cooled to temperatures just above absolute zero. At such extremes, the atoms behave not as individuals, but as a single quantum entity, a kind of superatom that exhibits coherent wave behavior. In 2010, physicists at the Technion Israel Institute of Technology created a beck in which sound waves could not escape from a central region, mimicking the event horizon of a black hole. And in 2016, a team led by Jeff Steinhauer reported something even more remarkable. They had observed spontaneous emission of correlated photons, the acoustic equivalent of Hawking radiation. These systems don't bend spacetime, of course, but they recreate the mathematics, the wave equations and causal boundaries that define a black hole's interaction with its environment. And over time, more experiments followed. In 2019, researchers at the University of Nottingham used flowing water and laser pulses to create optical analogs of event horizons and observe behaviors consistent with Hawking's predictions. These black holes could have been created with masses far smaller than any produced by stellar collapse. Some as small as a mountain, others as light as an asteroid. Crucially, their lifetimes depend on their initial mass. A primordial black hole with a mass of about 10-12 kilograms would evaporate over 13.8 billion years. The current age of the universe, while these experiments do not prove that black holes in space emit Hawking radiation, they confirm that the underlying physics is sound and observable, at least in carefully controlled conditions. This led to the black hole information paradox, a puzzle that remains unsolved to this day. Either Hawking radiation somehow carries the information back out, an idea many physicists now favor, or quantum mechanics itself must be revised. Neither option sits comfortably within the established framework of science. Over time, this would lead to a slow leakage of energy, and eventually, a complete evaporation. In its simplest definition, a black hole forms when a massive star exhausts its nuclear fuel and collapses under its own gravity. It unified quantum mechanics, thermodynamics, and general relativity in a single elegant prediction. But there was a problem. It was unobservable. The radiation emitted by a black hole via this mechanism is incredibly faint, orders of magnitude weaker than the cosmic microwave background. No telescope, no detector, no cosmic event offered the clarity needed. But something interesting began to happen. Physicists turned to the laboratory for black holes of stellar mass, let alone the supermassive ones at galactic centers. The evaporation process would take longer than the current age of the universe. So while Hawking's equations were admired, they were also shelved. Brilliant, yes, but untestable. Once something crosses the event horizon, it's gone forever. Energy, information, particles, all are swallowed without escape. The black hole may grow by accreting mass, may merge with others, may spin or wobble, but it does not get smaller. That was the dogma. If the mass is sufficient, the gravitational pull becomes so intense that not even light can escape. The boundary surrounding this region is called the event horizon, the point of no return. Inside, matter is compressed into what general relativity describes as a singularity, a point of infinite density, where the known laws of physics break down. According to Albert Einstein's theory, this structure is final. But Stephen Hawking's insight came not from the scale of general relativity, but from the unruly, unpredictable world of quantum mechanics. In 1974, he applied quantum field theory to the curved spacetime around the event horizon, and uncovered a startling contradiction. The vacuum of space, according to quantum theory, is not empty. It constantly churns with virtual particle and anti-particle pairs, blinking into and out of existence in the blink of a quantum eye. Normally, these pairs annihilate each other almost instantly. But near a black hole's event horizon, something different happens. Hawking realized that, occasionally, one of these particles could fall into the black hole, while the other escaped. This phenomenon, now known as Hawking radiation, was revolutionary. Still, the implications haunted physics. As the years passed, efforts to detect Hawking radiation directly stalled. If we can't observe black hole evaporation in space, perhaps we can simulate the conditions that allow it to occur. And so, in the early 2000s, a new field was born: analog gravity. One of the most promising platforms emerged from an unexpected material: Bose-Einstein condensates. The result was controversial. Some physicists questioned the interpretation, others the methodology, but the paper was peer-reviewed, the data robust. These lab results renewed interest in the real thing. Could there be black holes small enough, faint enough, ancient enough to be finishing their evaporation right now, somewhere in the universe? Enter the idea of primordial black holes, hypothetical objects formed not from collapsed stars, but from density fluctuations in the early universe. Just moments after the Big Bang, these black holes could have been created with masses far smaller than any produced by stellar collapse. Some as small as a mountain, others as light as an asteroid. Crucially, their lifetimes depend on their initial mass. A primordial black hole with a mass of about 1,012 kilograms would evaporate over 13.8 billion years, the current age of the universe. Which means, right now, if such black holes exist, some of them should be reaching the end of their lives. As the mass shrinks, the temperature of the Hawking radiation increases, rising inversely with the black hole's size. Toward the end, the black hole would emit high-energy gamma rays, part antiparticle pairs, and finally explode in a brilliant, sub-second flash. Since the 1990s, satellites like the Fermi Gamma Ray Space Telescope have detected short-duration gamma ray bursts, flashes of high-energy light lasting less than 2 seconds. Most are believed to originate from neutron star mergers or magnetar activity, but a small percentage, less than 1%, remain unexplained. Some researchers have speculated that these bursts might be final evaporation events of primordial black holes. So far, no candidate has matched all expected signatures, but the search continues. An inference: one thing is certain, we are no longer asking if black holes evaporate. It wouldn't be a supernova, but a kind of miniature Hawking nova, bathing a region of space in a sudden surge of radiation. It was a turbulent cauldron of energy, hot, dense, expanding rapidly, with fluctuations in pressure and matter so extreme that they might have spawned one of the most elusive and hypothetical objects in modern astrophysics: primordial black holes. And what would that look like? Unlike the supermassive black holes that take trillions of times the current age of the universe to meaningfully shrink, not only do they offer a potential way to detect Hawking radiation indirectly, but they also intersect with one of the biggest mysteries in modern cosmology. PBHS, depending on their mass and abundance, could contribute to, or even fully account for, the invisible matter that makes up roughly 85% of the universe's mass. Though observational constraints have ruled out PBHS as the dominant form of dark matter across many mass ranges, there remain windows of possibility, gaps in our data, where they might still be hiding. A PBH with an initial mass of around 5-10 kilograms would, according to the math, complete its evaporation today. While no conclusive detections were made, the study found several candidate bursts with spectral characteristics and durations that could match theoretical predictions. The rarity and randomness of these events made it difficult to confirm anything, but the door remained open. In recent years, gravitational wave observatories like LIGO and Virgo have detected dozens of compact binary mergers, most involving black holes of around 30 But in 2020, a detection was made that defied expectations: GW190814, a merger between a 23 solar mass black hole and an object of about 2.6 solar masses, an ambiguous mass that falls in the so-called mass gap. Too heavy for a neutron star, too light for a typical black hole. Some theorists propose that the lighter object could be a primordial black hole. These cosmic relics, if they exist, may be finishing their life cycles as we speak, emitting their last pulses of high-energy radiation before fading completely from existence. While gravitational waves don't tell us if a black hole is evaporating, these events suggest that unusual compact objects are out there, perhaps leftovers from the early universe, perhaps dying faster than we expect. The study proposed that a population of evaporating PBHS could account for a portion of the observed gamma ray background, the diffuse glow of gamma rays coming from all directions in the sky. Though this interpretation remains controversial, it reinforced the idea that black hole evaporation might be detectable not as a singular event, but as a statistical excess in the background radiation, the burst's hard energy spectrum, an isolated occurrence. It didn't behave like a magnetar flare or a typical short GRB. Some speculated quietly that it might have been a PBH death, though no follow-up confirmation was possible. A PBH evaporating near the end of its life would emit a final flash of gamma rays, possibly accompanied by electrons, positrons, and neutrinos in a sub-second burst. Even under optimistic scenarios, Perhaps one per year would be visible within the Milky Way, and the vast majority would occur in the distant universe, where the energy is redshifted and diminished. To catch one would require a combination of luck, continuous observation, and sensitive instruments tuned to the right range. Fermi detects and catalogs thousands of gamma-ray bursts, most of which are attributed to known astrophysical phenomena like neutron-star collisions or magnetar outbursts. However, there exists a small subset of very short-duration gamma-ray bursts events that last less than 0.1 seconds and do not seem to fit neatly into any known category. The radiation would be extremely energetic, and extremely. If a particular pocket of matter happened to exceed a critical threshold in density, compressed enough to overcome internal pressure and expand slower than the surrounding universe, it could undergo gravitational collapse. Their sizes could vary enormously, from as small as the Planck mass to as massive as 100,000 times the Sun. But perhaps most interesting were the PBHs on the low end of the mass spectrum, the ones that, according to Hawking's evaporation theory, should have evaporated by now, or be in their final moments of decay. The result, a black hole, born not from a star, but directly from the fabric of the early cosmos itself. In theory, the final moments of black hole evaporation would be spectacular, but have we ever seen one? That's the mystery. Meanwhile, the Large Hadron Collider at CERN has conducted experiments aimed at detecting microscopic black holes, hypothesized by some extensions of string theory. These tiny objects, if produced, would evaporate almost instantly via Hawking radiation. No such black holes have been observed, placing constraints on certain models of quantum gravity, but the possibility remains tantalizing. So today, we find ourselves at a unique juncture. We know the math works. We've built machines that replicate the behavior. We see hints in the sky, flashes and bursts and irregularities that defy easy classification. And behind all of it, the quiet voice of Hawking's insight still echoes. Black holes aren't black. They glow, faintly, and in the end, they vanish. Whether we witness that final flicker with our own eyes, or only glimpse it through instruments, we are asking where, and when, and how soon we will catch one in the act. In the vast early moments after the Big Bang, when the universe was less than a second old, it was far from empty. Unlike the black holes formed from the death of massive stars, these objects were theorized to form from overdense regions in the primordial plasma of the early universe, proposed independently in the 1970s by Yakov Zeldovich and Igor Novikov in the Soviet Union, and later by Stephen Hawking and Bernard Carr in the West. Primordial black holes represented a radical departure from known physics. Here's why this matters. The smaller a black hole is, the faster it evaporates via Hawking radiation. This makes primordial black holes a prime target for observational astronomy. So, how would we know if one is out there? And diet, the key lies in the energy signature. Since 2008, the Fermi Gamma Ray Space Telescope has been scanning the sky for these kinds of events. In 2018, a paper led by astrophysicist Charles Dermer analyzed over a decade of Fermi data, looking for PBH evaporation signatures. Even more intriguing was a 1997 analysis of data from the instrument aboard the now decommissioned Compton Gamma Ray Observatory. While gamma ray detectors remain our best bet for direct observation, other methods are being explored. Another detection, GW200105, involved an object that may also sit within this mysterious range. And what if the final moments of PBH evaporation have already been observed, but simply misunderstood? In 2019, Fermi recorded a peculiar gamma-ray burst lasting just 50 milliseconds, with no afterglow or host galaxy detected. The difficulty, of course, is that these final bursts are expected to be exceedingly rare. This is why new efforts are underway to expand our observational reach. Projects like Eostroga, Mamago, and future gamma-ray detectors aim to increase our sensitivity to transient events in the Mavigiv range, precisely the window where evaporating PBHs are expected to shine. But there's another frontier, looking not for the event itself, but for the after. If PBHs are evaporating in large enough numbers, they might leave a cumulative signature in the form of cosmic ray fluxes, or anomalies in the extragalactic background light. These indirect clues could help build the statistical case for their existence, even if we never catch one in the act. For now, the cosmos remains frustratingly quiet. No confirmed detection of Hawking radiation has ever been made. Can we recreate its conditions here in controlled environments and observe its analog? No PBH has been indisputably identified, but the search continues, driven by a sense of curiosity, urgency, and the lingering feeling that somewhere out there, one of the universe's oldest inhabitants is taking its final breath. And those tools came from one of the coldest places in the known universe, Bosenstein. Under these extreme conditions, the particles lose their individual identities and behave as one unified quantum wave function. In essence, it becomes a superfluid with properties so coherent that sound, light, and quantum phenomena can be controlled and studied with exquisite precision. And if we happen to be looking at the right place, at the right moment, maybe, just maybe, we'll catch it blinking out of existence. The goal isn't to create an actual black hole, of course. He created a flowing beck with a region where sound waves could not escape an acoustic analog of a black hole horizon. Over the course of many repetitions, his team observed spontaneous pairs of phonons, one inside the horizon, one outside, with correlations matching what Hawking radiation would predict. In one such experiment, a moving pulse of light altered the refractive index of the fiber in such a way that slower-moving photons were trapped behind it, mimicking the formation of a light-trapping surface. Researchers from the University of Glasgow and others have detected photonic radiation with statistical properties consistent with Hawking's predictions. In 1981, physicist William Unruh proposed that a supersonic fluid flow could mimic the physics of an event horizon. One particle in the pair appeared to carry away energy, while the other was trapped, and has since formed the foundation for a new class of tabletop black hole analogs. These experiments can't replicate the curvature of spacetime itself, but they successfully mirror the quantum behavior at a horizon and provide critical clues about how information and radiation might behave near real black holes. Importantly, the measurements showed entanglement between the two, a quantum signature expected in real Hawking radiation. Imagine water flowing down a drain. If the flow exceeds the speed of sound in a particular region, phonons, sound wave particles, inside that region cannot travel upstream. They help in to answer one of the most profound questions in quantum theory. Is Hawking radiation truly thermal, or does it retain quantum information? They are effectively trapped. This boundary behaves like an acoustic event horizon. If this holds true for real black holes, it could mean that Hawking radiation isn't random. It could carry the memory of everything the black hole once consumed. If the radiation is purely thermal, it means information that falls into a black hole is lost forever, violating one of quantum mechanics' most sacred principles, the unitarity of evil. But if even a sliver of that information escapes, perhaps encoded in subtle quantum correlations, then black holes may not destroy information at all, but simply scramble and release it slowly. While no matter what light is involved, the mathematics describing the system is nearly identical to those of a black hole. If Hawking was right, and black holes evaporate via thermal radiation, then what happens to the information encoded in the matter that falls in? And even provide a working model for how information emerges from the death of a black hole. Though we can't yet peer into an evaporating black hole in space, we can watch its shadow in the lab, flickering gently under the careful eye of quantum precision. Quantum mechanics says it must survive, but general relativity suggests it's gone forever. This conflict lies at the intersection of the two most fundamental theories we have, and resolving it may unlock the long-sought path toward quantum gravity. But to reproduce the behavior of event horizons, particularly the conditions under which virtual particles split and one escapes, that's where Hawking radiation is expected to originate, and it is also where the lab becomes our telescope. It may be a sound wave in a chilled chamber in Israel, but it tells us something profound about what might be happening around Sagittarius, Astris, or in the final seconds of a primordial black hole's life. While black hole evaporation remains out of reach in the cosmos, scientists have turned inward to earthbound laboratories to investigate one of the boldest ideas in modern physics. If we can yet detect Hawking radiation in space, this question lies at the heart of a rising frontier in experimental physics called analog gravity, a field that seeks to model features of curved spacetime using other physical systems. One of the earliest breakthroughs came not in astrophysics, but in fluid dynamics. Unruh's idea sparked decades of experimentation, but it wasn't until the 21st century that experimental physicists found the tools precise enough to test it. A beck is a state of matter formed when a gas of bosons is cooled to temperatures just a few billionths of a degree above absolute zero. In 2016, physicist Jeff Stinhauer at the Technion Israel Institute of Technology published a landmark study. Though the radiation was acoustic, not electromagnetic, the principles were strikingly parallel. This wasn't just a fluke. Steinhauer's work was peer-reviewed, replicated with modifications. Similar efforts have taken place in optics, using laser pulses and nonlinear fiber to simulate horizons for light. Other analog platforms include superfluid helium, where variations in flow velocity create acoustic analogs, water tanks, where surface waves mimic horizon structures, ion traps and quantum circuits, engineered to simulate curved space at the level of quantum entanglement. These systems don't just provide insight into black hole physics. That distinction matters immensely. Steinhauer's experiment in 2019 showed entanglement across the acoustic horizon, a crucial sign that quantum correlations survive the horizon formation. This ties directly into one of the most heated debates in theoretical physics: the black hole information paradox. It's the paradox that has split the field for decades, and that's where the lab becomes more than a curiosity. It becomes a window into the unification of physics. If lab-made analog black holes exhibit information, preserving Hawking radiation, then we are seeing, in real time, how the quantum world might heal the fractures in our cosmic understanding. In fact, some researchers now propose that analog experiments might advance faster than space-based observations, and even provide a working model for how information emerges from the death of a black hole. Though we can't yet peer into an evaporating black hole in space, we can watch its shadow in the lab, flickering gently under the careful eye of quantum precision. But even this isn't the limit. New hybrid experiments are underway that combine analog gravity with quantum computing, using controlled entanglement and artificial quantum systems to simulate Hawking, evaporation, and information flow, but in milliseconds, letting us compress cosmic-scale processes into the flicker of quantum logic gates. At IBM and Google, teams are exploring whether black hole analogs can be embedded into qubit matrices, effectively building digital models of black hole entropy. But today, by cooling atoms, shaping fluids, and guiding photons, we're bringing their secrets to Earth. The same physics that governs the end of stars now ripples through sound waves in labs, through circuits of superconducting qubits, and pulses of light in fiber optics. In 2020, a team led by Stanford's Harlow and Preskill published a theoretical blueprint for using quantum circuits to replicate the page curve, the mathematical representation of how information might re-emerge during evaporation. If realized, this would mean that quantum simulators can reproduce the entire lifetime of a black hole, not in eons. In all this, we find a strange reversal. Black holes were once the most inaccessible things in the universe, locked away behind lightless horizons. Each of these steps is a translation, from space-time to system, from theory to measurement, from the infinite to the tangible. And with each translation, we inch closer to the truth. That black hole evaporation isn't just a poetic idea or a theoretical ghost. This pulse would be bright in the gamma-ray spectrum, incredibly short-lived, and statistically rare. As the mass of APBH shrinks, its temperature rises dramatically. Hawking's equations show that the temperature of a black hole is inversely proportional to its mass. This means that as it becomes lighter, it gets hotter, and this process accelerates exponentially toward the end. And some have occurred with spectral hardness ratios, a measure of photon energy that align remarkably well with the decay curve of a black hole in its terminal phase. For a PBH with an initial mass of 10 kilograms, there's also the sheer difficulty of localizing these events. The evaporating primordial black hole hypothesis remains a valid interpretation, especially when considering that alternative explanations have not been conclusively demonstrated. Gamma-ray detectors, unlike optical telescopes, often have large error boxers, meaning the exact origin of the signal is hard to pin down. For instance, an evaporating black hole may also emit cosmic rays, particularly electrons and positrons, in its final phases. Instruments like AMSO-2 on board the International Space Station and the Pierre Auger Observatory in Argentina have reported anomalous positron excesses, more antimatter particles than expected. If one of these were to evaporate fully, the combination of gravitational waves followed by a gamma-ray flash could provide a multi-meson confirmation of black hole evaporation. In 2019, researchers analyzing LIGO data proposed that a small subset of black hole mergers involved objects with masses that could be consistent with primordial origin. These observatories would have better localization, higher sensitivity, and continuous coverage. They are designed with fast transients in mind, and may be the first instruments capable of not just detecting, but truly resolving an evaporating black hole event. These are lower than expected from stellar collapse, and may point to an exotic population of black holes formed in the early universe. New simulations incorporate the full suite of particle emissions, not just photons, but hadrons, neutrinos, and even supersymmetric partners, if such particles exist. These simulations help narrow down the expected signature of a PBH's final second. And if nature is kind, that signature will one day match a real burst caught in the atom. While many suspect pulsars or dark matter annihilation as the cause, PBH evaporation is still on the list of possibilities, especially if the PBHs are small and numerous. Without an optical or X-ray, astronomers can't triangulate the burst's location, confirm its host galaxy, or determine its distance. The black hole may transition into a Planck star, a theoretical object proposed by loop quantum gravity, where quantum repulsion halts the collapse and triggers a bounce, an event that might unleash a gamma-ray burst from deep inside the horizon, visible in our universe. Does it leave a stable remnant? Does it release a final catastrophic burst? Or does it enter a new phase of existence altogether? So even when a candidate via its final second could produce a burst of gamma rays comparable in intensity to some of the brightest events in the universe, though on a much smaller scale and time, but the possibility of detecting such an event is no longer science fiction. In fact, some believe we may already have seen one, or several without realizing it. These are events shorter than 0.1 seconds, with no discernible afterglow or host galaxy. They are bright, sharp, and unexplained. In 2018, a group of researchers from NASA and several universities published a statistical study of these ultra-short events. They proposed that at least some of them might match the expected signal from an evaporating PBH, with energy profiles and timescales consistent with theoretical models. It's a process, it's happening. And among them, the Pharma Gamma Ray Space Telescope, launched in 2008, remains the most capable of detecting such flashes. Pharma continuously surveys the sky, capturing high-energy photons and logging transient events, brief flashes of gamma radiation that may last milliseconds or several seconds. Most are classified as gamma-ray bursts, and they typically fall into two categories: long G, often associated with collapsing massive stars, and short GRBs usually attributed to neutron star mergers. And in a very real sense, we are watching it unfold, not with our eyes, but with instruments tuned to the very breadth of the universe itself. Even as laboratory experiments provide glimpses into the microcosmic analogs of black hole evaporation, the question that lingers is perhaps the most tantalizing. Can we observe this phenomenon somewhere in the cosmos for real? The short answer is, maybe. If primordial black holes are evaporating today, as theory allows, then somewhere in the universe, a dying black hole might be sending out a last desperate pulse of radiation. To understand what an evaporating black hole might look like from Earth, consider its final seconds. This is exactly the kind of signal that gamma-ray telescopes have been scanning for, but a tiny fraction, less than 0.1% of all recorded bursts, fall outside either class. These events are known as very short gamma-ray bursts. They don't repeat, they're not localized to any known galactic structure, but there's a problem, a big one. Gamma-ray bursts can be deceptive. Some terrestrial phenomena like lightning and upper atmosphere electrical discharges can mimic their signals. And yet, the frequency of these events, estimated at about 1 per year per cubic gigaparsec, is not inconsistent with predictions based on PBH formation models. Beyond gamma-ray bursts, some scientists are exploring other potential observations. Another promising approach lies in gravitational wave detection. While black hole evaporation doesn't itself emit gravitational waves, the mergers of primordial black holes might. Although not directly tied to Hawking radiation, such objects could be in the later stages of their lives, with evaporation already underway. But perhaps the most extraordinary search strategy is now unfolding in the planning documents of future observatories. The proposed Eostrogam and Imago missions aim to vastly improve our ability to detect MEV, GeV, gamma rays, the energy range where PBH final evaporation is most likely to occur. Meanwhile, theoretical models are becoming more sophisticated. Still, the question lingers: what happens at the very last moment? When a black hole shrinks to near zero size, does it vanish? Some quantum gravity theories suggest that as a black hole nears Planck-scale dimensions, classical notions of space and time break down. The black hole may transition into a Planck star, a theoretical object proposed by loop quantum gravity, where quantum repulsion halts the collapse and triggers a bounce. An event that might unleash a gamma-ray burst from deep inside the horizon, visible in our universe. This would explain why some bursts appear to come from nowhere, without progenitor stars or host galaxies. They may not be happening in our universe's present, but echoing from deep time, leaking through as the black hole's interior is exposed in its final gasp. And so the search continues. A careful, patient vigil for a signal that may last just milliseconds, but would rewrite everything we thought we knew. Still, no confirmed observation has yet matched the full criteria of such an event. Because to catch a black hole in its final breath would not just be a scientific triumph, it would be a moment of witnessing the death of something that defies death. An object that swallowed light, warped time, and endured for billions of years. And in that moment, if we're lucky enough to see it, we won't just be watching something vanish. It's a confrontation with the boundaries of knowledge itself, with the most sacred assumptions about permanence, time, entropy, and information. When something falls into a black hole, all that remains to the outside world is mass, charge, and spin. No trace of the object's original properties survives. A book, a planet, a star, all are reduced to the same silent imprint on the curvature of space. Others argued that the radiation somehow carries the information out, albeit in a scrambled form. Hawking himself, near the end of his life, shifted his stance, suggesting that quantum fluctuations at the event horizon might encode the information in subtle correlations within the Hawking radiation itself. If the black hole eventually evaporates, and the radiation it emits is purely thermal, as Hawking first calculated, then the detailed information about what fell in is lost forever. Elegant delete, deeply supported by quantum gravity models, but unconfirmed by observation. That's why the hunt for a real black hole in the act of evaporation is so vital. Even Sagittarius A*, the supermassive black hole at the center of our Milky Way, with its 4 million solar masses, will one day shrink, dim, and vanish. Not soon. Not even within trillions of years. But eventually, the universe will become increasingly empty, as even the black holes wink out one by one. This era has a name, the black hole era, followed by the dark era, when only thin radiation and stray particles remain. It could validate or shatter decades of assumptions. It is the quiet, patient engine by which entropy completes its work. It turns mass into energy, form into formlessness, presence into echo. If Hawking radiation is real, and if even one black hole somewhere in the observable universe is evaporating right now, then the implications reach far beyond astronomy. They challenge the very foundation of physics. One day, not even a black hole, what remains may not be darkness, but a soft and silent light. A memory of math, a pattern of energy, a whisper of what once was. Escapes the pull of time. Slow down. Let the stars fade into the distance. Let the last embers of that ancient singularity dissolve into silence. Imagine a place where even gravity loses its grip, where light, space, and matter come undone. The echo of Hawking's vision still hums quietly across the void. Not loud, not urgent, but steady. We may never see a black hole evaporate with our own eyes, but we now know that if the universe waits long enough, it will. And when it does, not more. In silence, in the slow, our instruments will catch that trace. Perhaps we'll see the moment when light, once trapped forever, returns. And in that flash, however brief, we will find the closing of a loop, the fulfillment of an idea, the gentle unraveling of what we once thought was eternal. If information is preserved in Hawking radiation, if the echoes of fallen stars, shattered worlds, from Stephen Hawking's first calculation in 1974 to modern laboratory analogs, from the faint hope of a dying PBH to the cosmic whispers of the far future, we see a narrative emerging, not of destruction, but of transformation. And vanished particles are encoded in the final light. Then the universe doesn't forget. It remembers, not in language or memory, but in the quantum fabric itself. We'll be watching the universe whisper one of its deepest secrets, through radiation, through silence, through light that came from the edge of time itself, proposed by Elmhiri, Merleff, Palkinski, and Sully. It argued that if information is preserved and accessible in the radiation, then the smooth fabric of space-time at the event horizon must be violently disrupted. A final trace that ripples out into the universe long after the object itself is gone. A fallen observer would encounter a wall of high-energy particles, a firewall, contradicting general relativity's predictions of a benign crossing. This conflict between quantum theory and classical spacetime became emblematic of a deeper tension, the incompatibility of our two most successful theories. The deeper we chase the mystery of evaporating black holes, the more it becomes clear. This is not just an astrophysical curiosity. In 2019 and 2020, researchers from Caltech, Stanford, and MIT, including Ahmed Almheri and Jeff Pennington, produced groundbreaking calculations using quantum entanglement and replica wormholes in a model called ADD's CFT correspondence. Their result? They derived the Page curve, a predicted graph of entropy emission from a black hole, which showed that the radiation begins as thermal, but then declines, preserving information after a certain point. This was the first strong theoretical evidence that information may indeed escape, consistent with unitarity. Let's start with the most immediate, the preservation of information. In the quantum world, the rule is absolute. Information cannot be destroyed. This isn't philosophy. It's baked into the mathematics of quantum mechanics. Every process, no matter how chaotic, is governed by unitary evolution, a principle that ensures that the past, present, and future are connected in a way that never discards the full record of what came before. But black holes seem to break that rule. This is the essence of the black hole information paradox, and it has become one of the most fiercely debated questions in all of theoretical physics. For decades, camps split across theoretical lines. Some believed information was truly lost, and that quantum mechanics needed to be revised. In 2004, the famous black hole firewall paradox deepened the mystery. Yet even amid the debate, progress was made. But here's the catch. All of this remains theoretical. And that brings us to the long-term implications. If black holes do evaporate, then no black hole, no matter how massive, is eternal. In fact, if Hawking radiation holds true, then the fate of the universe itself is altered. In the far future, beyond the last stars, beyond the last white dwarfs, all black holes will begin to evaporate in earnest. In this endgame of cosmic history, Hawking radiation becomes the final process that shapes reality. It is in a very real sense how the universe says goodbye. And yet, embedded in this farewell is something extraordinary. The possibility that nothing is truly lost. This idea brings us full circle. A black hole doesn't end with a bang. It ends with a message, a glow, and perhaps, now, imagine a place where even gravity loses its grip, where light, space, and matter come undone. The echo of Hawking's vision still hums quietly across the void, but steady. We may never see a black hole evaporate with our own eyes, but we now know that if the universe waits long enough, and when it does, it will not roar. It will whisper, in radiation, in silence, in the slow, final breath of a dying giant.